Welcome to the debate. 100 years ago, roughly in the summer of 1925, Werner Heisenberg formulated the first full version of quantum mechanics, and today, well, it remains the most successful theory in physics, underpinning everything from, atomic clocks to quantum computers. Yet, as physicists gathered recently on the island of Helgoland to celebrate its centennial, a really profound question persists. What does quantum mechanics truly tell us about the nature of reality itself? Is the quantum state, often written as psi, is it a description of an objective reality that exists independently of observation, or is it fundamentally a representation of an observer's information, maybe their belief about the world? So today, I'll be arguing that the quantum state is best understood not as a direct picture of reality, but, well, more as a representation of an observer's knowledge and beliefs. It's like a user's manual, if you will.
Right. And I'm going to contend that while it's incredibly practical, a truly fundamental theory of nature has to describe an objective aspect of reality, independent of any observing agent. I think the quantum state, psi, points to something real, even if that reality turns out to be stranger than we might expect.
Okay, so my perspective is that quantum mechanics, and particularly this quantum state psi, it serves primarily as a kind of user's manual for navigating reality. It's not really a direct snapshot of an independent, objective physical world. I mean, think about Heisenberg himself. When he developed the theory, he famously gave up the mental image of atoms having fixed parts. He focused instead on what could be observed, what could be measured. This highly pragmatic stance, it's echoed really powerfully in the Copenhagen interpretation, which was one of the earliest and frankly most influential frameworks for quantum mechanics. Niels Bohr famously stated, "There is no quantum world, there is only an abstract quantum mechanical description." Now, from this viewpoint, psi isn't a blueprint of some fixed underlying reality. It's more like a catalog of potentialities, possibilities that we can interact with. Chris Fuchs, a pioneer of QBism. That stands for quantum Bayesianism, which is a modern interpretation that views quantum states as subjective information. He puts it beautifully. He says a quantum state is a catalog of my degrees of belief about the consequences of my actions. See, this emphasizes that the theory is fundamentally about us making decisions, placing smart bets, and understanding the world through our interactions. We are in the world, pushing it around, seeing what it does back to us, and phi is essentially our representation of that interaction.
I appreciate that pragmatic approach, and you're right, the success of quantum mechanics is just undeniable. But while acknowledging its immense practical power, I find the notion that psi merely represents information or belief, while it feels deeply unsatisfying for a fundamental theory of nature. For me, the measurement problem really stands as a glaring testament to this inadequacy. This is the central puzzle, right? If psi describes multiple possibilities before an observation, how does the act of measurement mysteriously somehow collapse it into the single concrete reality that we all experience? Nicholas Giesen, a prominent physicist, he points out quite aptly that without a resolution, quantum theory is not physics. Even Einstein, expressed profound unease. He noted that quantum mechanics seem to speak only of what we know about nature and no longer about what nature really does. So my perspective aligns with that search for a description of how nature does it, independent of any observing agent. And look, the historical disproving of Einstein's specific hidden variables, these were, hypothetical, unknown properties meant to make the world deterministic. The fact that Bell's experiments ruled those out didn't negate the need for a more objective reality. If anything, it showed that reality itself is stranger than expected. It pointed to a fundamental non-locality or maybe a lack of fixed properties until measurement. And that just makes it all the more critical, I think, to understand what psi truly represents about this independent reality.
You rightly bring up the measurement problem. And yeah, it's certainly an essential challenge for any interpretation. But from my perspective, this collapse of the quantum state, it isn't actually a physical event happening out there in the world itself. It's not like the universe suddenly shifts gears or something. Rather, it's an update of an agent's knowledge or belief when new information is gained through interaction. The possibilities don't just vanish from some objective external reality. Instead, our understanding of what's possible simply narrows based on the outcome we observe. This, I think, elegantly avoids that uncomfortable question of why a measurement device acts unquantum-like. Because the change isn't in the external world itself, it's in the observer's state of information. When you interact with the system, your knowledge about it instantly becomes more specific, right? And those other future possibilities, they vanish from your perspective because, well, they're no longer relevant to your updated state of information.
I'm sorry, but I just don't buy that it's just about knowledge. If collapse is solely about an update of information, it completely fails, in my view, to explain the empirical reality of a single, definite outcome in an experiment, an outcome that every observer agrees on. The core of the measurement problem, as I see it, asks this: why does the psi for an electron collapse when it interacts with a macroscopic machine, giving us a specific, undeniable result, but not when it interacts with another electron? In that case, it just continues to behave quantum mechanically. This implies a profound physical distinction in the interaction, doesn't it? And that's something an information-only view really struggles to account for. QBism insists, and I tend to agree, that physics is all about extracting information about how nature does it. Nature, not agents. He hopes a resolution will eventually reveal that measurements have one unique objective outcome, independent of any agent's knowledge or belief. The sheer definiteness of the observed world, it just points to something more than just our perspective.
Okay, I understand your demand for that definite objective outcome. But consider this. The definiteness you experience is a consequence of your interaction. The electron doesn't collapse for another electron, as you said, because they are both quantum systems. They're interacting in a way that preserves quantum superposition, just within a larger entangled state. It's only when a sufficiently complex, classical-like system, like a measurement apparatus, interacts with it, and that information becomes accessible to you, the agent, that your information state updates. That leads to your perception of a definite outcome. The universe doesn't pick an outcome. You register one. It's fundamentally a relational process, I think, not some objective collapse of the wave function that everyone somehow simultaneously observes in the exact same way.
But that still feels like it pushes the problem onto the agent, doesn't it? If the definiteness of the world depends on my information, how do we explain a shared, objective scientific reality where everyone agrees on the result? It feels a bit like we're just, moving the goalposts instead of solving the core issue of why nature presents us with a single, unambiguous result from these inherently probabilistic quantum states. I mean, if the electron truly exists in multiple states, why do we never see it in multiple places simultaneously, even when our measuring devices are themselves ultimately made of quantum particles?
That's an interesting point. Yeah, it leads us directly into entanglement and Bell's theorem. Bell's theorem and the subsequent experiments verifying entanglement, they famously demonstrated these profound correlations between distant particles. Now, you might say this points to spooky action at a distance, as Einstein famously called it. But even these correlations, they can still be framed quite beautifully within an information theoretic view. For instance, Gilles Broussard, one of the co-inventors of quantum cryptography, and his collaborator Paul Raymond Robichaud, they proposed this parallel lives interpretation. It suggests that even with entanglement, all contact is fully confined to local space. What appears to be non-locality, that perplexing idea that distant, entangled particles can instantaneously influence each other, seemingly faster than light, well, it could be explained by a local splitting of observer bubbles, maybe, that later converge, maintaining a completely local understanding for the agents involved. These correlations are simply what we as agents observe and use to update our beliefs about entangled systems. It doesn't necessarily imply a spooky action at a distance occurring in some objective independent reality. It's more about how our information about these related systems becomes correlated.
That's a compelling argument for trying to maintain locality, I grant you. But I'd argue that Bell's experiments fundamentally force us to confront a deeper reality, not just
a shift in our information bubble. They proved, essentially, that either spooky action at a distance is real or the world lacks determined real properties until measurement. This wasn't just about what we know. It felt like a profound statement about reality itself. The fact that individual particles don't have these secret lives governed by Einstein's hoped-for hidden variables, those local deterministic properties, that implies, or at least strongly suggests, that psi serves as a complete description. And that pushes towards an interpretation where psi is a real physical entity, or at least it's indicative of an objective, deeply interconnected structure of reality.
To deny psi's reality entirely, I think, risks trivializing the profound implications of entanglement on the very nature of existence. It's not just our knowledge that's correlated, it's the outcomes, the behavior of the particles themselves, which fundamentally defy classical locality and determinism. That points to a deeper objective truth about quantum mechanics.
But hold on. The absence of those specific hidden variables doesn't automatically mean that psi must be objectively real in the way you're suggesting. It just means that any underlying reality, if it exists in that sense, must be non-local or non-deterministic in a way that Einstein found, well, unpalatable. My point is that the very meaning of non-locality can be reinterpreted. This parallel lives idea, for example, it suggests that the choices made by observers in these entangled experiments lead to local divergences in their experiences, which then somehow coherently converge. The apparent non-locality isn't some external force acting mysteriously. It's a feature of how information is processed and shared between agents who are operating within a quantum world.
Right. And that brings us right to the implications for reality itself and this notion of private worlds, which, frankly, I find deeply problematic. If, as you seem to suggest, information is so central and experiences are somewhat relative to the observer, well, where does that leave us?
Well, let me clarify. My approach doesn't deny a real physical world exists. Absolutely not. It rather clarifies that our direct access is always to our representation of it, which is generated by our interactions, as Fuchs points quite powerfully. I'm in the world. I play a part in it. I can't delete myself. This perspective, I think, avoids the ontologically excessive, postulating more fundamental entities than necessary, and maybe the psychologically unsettling implications of interpretations like many worlds, where literally all possibilities physically branch off into separate universes. Sure, it might lead to what some call private realities in certain extreme conditions, maybe like Carlo Rovelli's relational mechanics suggests. That's a framework where the quantum state of a system is always relative to another system, never absolute. But that's just a consequence, maybe, of accepting that information is relative to an observer. It's not necessarily a flaw. It's about clarifying our role within the universe rather than pretending we're somehow outside it, observing from some godlike vantage point.
I see why you think that, but let me give you a different perspective. If we accept private realities in any meaningful sense, how on earth do we reconcile our shared, consistent experience of a single, coherent world? Carlton Caves, a quantum information theorist, he expresses this frustration quite bluntly, saying, "It's just embarrassing that we don't have a story we can tell people about what reality is." And look, researchers like Gemma Delescoves and Robert Speckens are actively exploring how quantum-like effects could arise from an underlying classical reality, but where agents are simply ignorant of definite particle states. Delescoves, for instance, has shown that an agent effectively trapped inside the universe could perceive particles as having a quantum-like state with multiple possibilities, even if, from some hypothetical, godlike view outside, those particles have real specific positions.
This suggests that maybe the simultaneous possibilities of psi are actually an artifact of our limited perspective of being trapped inside, rather than an ultimate statement about reality itself. It points towards something more objective existing beneath our perceived knowledge. Surely, our shared reality implies some kind of shared underlying structure.
That's an intriguing line of thought, I admit. But I'd push back a little on the idea that our shared experience absolutely requires an underlying objective reality in the classical sense you mean. We share an experience because our interactions with the world, and crucially, with each other, are consistent. We calibrate our user manuals, so to speak, against each other all the time. The information we gain, the predictions we make using quantum mechanics, the outcomes we observe, these are all public and verifiable. So even if each of us constructs our own representation of reality based on our interactions, the sheer consistency of these representations, enforced by the mathematical rules of quantum mechanics, is what creates the strong impression, maybe even the function, of a single objective reality. It's a pragmatic and empirically consistent view, I maintain, even if it does challenge our deep-seated classical intuitions.
But the very consistency you speak of, the way those user manuals miraculously aligned for everyone everywhere, doesn't that itself imply a deeper shared framework, something that isn't just about our individual beliefs updating? Why would all these supposedly subjective updates of knowledge lead to the same predictable results every single time if there wasn't something fundamentally stable and objective about the universe they are describing?
That's a fair question, absolutely. And it brings us neatly to our final point, the search for a deeper theory. My position, fundamentally, argues that the theory we have works spectacularly well. The perceived problem is often more about our philosophical discomfort with it, our ingrained classical intuition demanding some kind of mechanical picture underneath. QBism, for example, it actively seeks to end these endless discussions about quantum foundations by providing a consistent philosophical framework for how we interact with the world through quantum mechanics. Fuchs apparently believes it's a public service to get rid of quantum foundations conferences, aiming to convince everyone of this informational answer before he dies. The beauty, perhaps, is in understanding the amazing user's manual we've been given, not necessarily in trying to unscramble an omelet that from this perspective was never meant to be unscrambled.
We might not need a deeper how nature does it if how we interact with it gives us everything we can predict and understand.
Okay, that's an interesting point. And I agree completely. The theory's predictive power is just unparalleled. However, I would frame the situation quite differently. Many physicists, probably most working on foundations, feel that quantum mechanics is missing something. And the pursuit of a deeper understanding isn't just philosophical hair-splitting. It feels like a scientific imperative. Think about Lucian Hardy and others. They believe that incorporating gravity, the only fundamental force we haven't successfully quantized, could lead to a conceptual bonfire, a radical reevaluation, basically, that might finally clarify quantum mechanics' meaning. If space and time themselves turn out to behave quantum mechanically, maybe with multiple contortions or possibilities existing simultaneously at the most fundamental level, well, that might force a more objective interpretation, perhaps even leading to an unambiguous reality, at least for space-time itself.
Speckins, too. He believes a new way of thinking about reality will have subsumed both classical and quantum physics. He suggests the core of reality might ultimately lie in causal connections, the fundamental relationships between events, moving us beyond these purely epistemic, knowledge-based views, or purely ontic, reality-based views of psi.
The historical drive for unification in physics, for a single coherent picture, it naturally pushes us towards seeking a more objective understanding.
I definitely recognize the profound appeal of a unified theory, of course. But from my perspective, the challenge might not be with quantum mechanics itself, but rather with our lingering classical biases. What if space and time are quantum? Then perhaps our everyday experience of a definite spacetime is also an emergent phenomenon, something relative to our interactions, rather than reflecting an absolute underlying objective grid. That conceptual bonfire you mentioned, it might lead not to a more objective psi, but perhaps to an even deeper appreciation of the role of the observer, the agent, and the fundamentally relational nature of reality itself.
Perhaps. But the very fact that we are searching for a quantum theory of gravity, for a fundamental description of the universe's very fabric, that implies an objective structure to be discovered, regardless of whether our subsequent observations turn out to be relative to that structure. It's an ongoing scientific quest for a deeper truth about what is.
Well, our discussion today, I think, really highlights the profound and clearly enduring disagreement surrounding the interpretation of quantum mechanics, even now, a century after its inception. We've definitely explored the tension between viewing the quantum state psi as fundamentally a representation of an observer's knowledge and viewing it as a description of an independent, objective reality.
Right. While your perspective emphasizes the undeniable power and consistency of an information-based understanding grounding quantum mechanics in what we can meaningfully know and predict. My arguments have tried to underscore the intuitive demand for a theory that describes how nature works, independent of our perception, and, the ongoing quest for a more complete objective picture.
Both positions, armed with, I think, compelling arguments and specific insights from many of the leading minds working in the field, hopefully leave us all with a deeper appreciation for the profound mystery that quantum mechanics still presents. The debate about what quantum mechanics truly means is clearly far from settled.
Absolutely. And the conversation continues to push the boundaries of our understanding of reality itself. There is certainly more to explore in the material, and we hope this discussion has illuminated some of those fascinating avenues.
Thank you for joining us on The Debate.